All right, so I want to go over polar coordinates and essentially go by the delta A, the change in area for A in polar coordinates has that extra R term in it. And we're going to do this two ways. This time we're going to just simply think about what's going on with that little, with the area, delta A. And essentially we're going to see that for polar coordinates, the size of delta A depends on position, and that's not true in Cartesian coordinates. So let's go ahead and look at some Cartesian coordinates. So go ahead and consider, so we're in the gray area, this is some shape we want to integrate over. Probably actually isn't the greatest for polar coordinates, but it's just a random shape. Now, I'm going to go ahead and let's think of, we've broken it up in Cartesian coordinates, and let's just go ahead and use the grid lines there and pretend that's our partitioning. So for instance, I can add, we can look at one small partition. And here delta x is this difference here, so delta x equals 0.2. Delta y, change in the height in that direction, is also 0.2. And so we've got a little square there, and that's our area. And notice that, of course, the area of this is just 0.2 times 0.2, 0.04. And notice that if my delta x and delta y don't change, it doesn't matter where we are. If we look over here at this orange delta A, it is the exact same area as our green. That is, the area is just delta x times delta y. And that's true in Cartesian coordinates. So it doesn't matter if where we place our little area, that basically if delta x is the same size and delta y is the same size, my delta area will be identical. That's not true with polar coordinates. So let's throw some polar coordinates here. So for instance, we're going to look at this little area here, which is between R1 and R2. So we've got delta R is that distance there. And it's between angle 1 and angle 2. And let's go ahead and throw those angles. So between, our delta theta, delta angle is between those two black lines. Delta R is between there. And we've got this little area, and it looks about roughly the same size as that, any of these Cartesian areas. But here's the problem. Now let's look at a different region. Delta theta will not change. It'll be the same change in angle, and it'll be the same change in radius. We're out here. So the change in R is still about the same. All right, it's still the same. It's a change of R changed by 0.2. The angle is still the same, but obviously this area is bigger. We know that this length, the length of that arc for that same angle is obviously longer if you're farther from the center, if the radius is longer. So this area is much bigger than that area. And that's the problem, is the deltas are the same. Delta R is the same, delta theta is the same. So this delta theta and that delta theta are the same. It's the same amount of change. That delta R and that, the red delta R and the blue delta R are also the same. But obviously the areas are not the same. Well, what's the scaling factor? That's where the additional R comes in. That is, this area is R times, and R is going to be the average between these two. And basically you think of R as right in the middle. That is, this area will be R times as big as this area. And that's where that extra term comes in. It's basically a scaling factor. So that's the first way we can think about it. Later on, when we talk about transformation of variables, we'll have a more general way. This is basically the understanding fix for polar coordinates, and we can generalize such concepts to other coordinate systems. And we'll do that at some other time. All right, thank you very much.